Next, we'll be talking about B-plus trees. So this is an example of a B-plus tree, and a B-plus tree is a type of index. And an index is a data structure that allows us to do some quick lookup on our data. So B-plus tree has two types of nodes. First, we have leaf nodes, and these are nodes at the bottom of the tree, denoted here in the blue, and these contain data entries. Our second type of node is our inner nodes, and these are nodes not at the bottom of our tree, and this is denoted with the purple ones here, and these are solely for lookup. So no data entries are stored in these. Couple of notation, we have D to denote the order of the tree, and so each node contains up to 2 D values. So for this B plus tree, we note that each has 4 values, so our D would be 2. So we would say the order of this tree is 2. And note that inner nodes have a maximum fan out of 2D plus 1, so each inner node can have 2D plus 1 children. And we see that in the purple one, where our D is 2, so it can have the max number of children as 5, and we see that here. A key invariant for a B plus tree is that for a value x in the inner node, the corresponding subtree only has values greater than x, greater than or equal to x. So for example, if this number was 5, then any values here in this subtree would have to be greater than or equal to 5. And then we have height. So this is the numbers it takes to get from root to leaf. And so for this example, the height would be 2. Alternatively, you can think about this as the number of inner node levels in the tree, because 1, 2, or 1, 2 from root to leaf. So index types. How is data stored in the index? So we have 3 ways that we do this. Alternative 1, we store the actual records in the index. So in our leaf nodes, we have our actual records. Alternative 2, we store the key and record ID in the index. And in alternative 3, we store the key and a list of matching record IDs. So that looks something like this. Note that in this leaf node, this is our data page, and so our data page has the actual records themselves. In alternative 2, what we have is we have the key and we have a pointer to the data page where the value is stored at. And in alternative 3, we have the key and a list of pointers to the data page where it's stored at. And note that alternative 3 would be more compact than alternative 2 if we have a lot of duplicates. One other thing with these alternatives, if you have an alternative 2 or 3 tree, you can have either what we call a clustered or an unclustered index. So what clustering means is that the actual data is roughly sorted in order of the search key, and unclustered means that it is not in order. And so that will look something like this. So now inserting into a B plus tree. Well, how do we do that? Well, we first start off by looking for the correct leaf node by looking through our inner nodes. And so we see here that 25 is greater than 24 and less than 30. And so we would look at this leaf node and then we'd insert it if there's room. And so in this case we do, so we just add the entry. And then we keep the leaf sorted. Now, what if we want to insert 8? Well, if we followed where we should do it, it's less than 13, so it should be this leaf node. And if we want to insert 8, there's not enough room. So what do? Well, we split the leaf into 2 leaves with D and D plus 1 entries. So it looks something like this, where we have 2 values for D, and D plus 1 is 3, and so we have these 2 leaf nodes. And now we copy up the middle key, so in this case it'd be 5, to the inner node. And this is because leaf nodes have data, so we don't want to lose it. And then if the inner node is full, like it is in this case, then we want to do something similar like that we did to the leaf nodes. And so we split the inner node into 2, but instead of copying up the middle value, we push it up. And this is because inner nodes don't have any data, so there's no point in copying the key. So what we do here is we split these into 2, so 24 and 30 move, and then we have 5 and 13 here, and then we push up the middle node. So now that 17 is our parent. And yeah, that's it. We also have a rough table for the runtimes for the differences between heap, sorted, and clustered indices. And feel free to view the lecture and the notes if you want to see how these numbers were exactly calculated.